Okay, so we did the magnesium lab, and we went over those lab calculations. Is that right? So we just need to go over the nail calculations. So that starts down here. Okay. Some of these things. Let's see. Observation before. Okay, so we're looking for mass of copper produced. So hopefully you've already done this, but you're going to take the mass of the dry copper and the mass of the beaker, which is what you should have measured today. You're going to subtract off the beaker mass, so hopefully use the same beaker, and that will be the mass of the copper produced. Okay, and how are we going to figure out how much iron was used? Yes, mass of nail before and after. So after, it should have gotten smaller. Some of us had something weird happen. So you're going to take after minus before. The nails kind of shrunk, so that is going to be the mass of the iron that you use. We're going to assume that. And then we need to figure out moles of copper and moles of iron. So how do we do that? Yes, use the atomic weight. Perfect. And what do we do with that?
Times or like you times it by so I guess you can write that.
Yeah, yes. So perfect. So let's write it out how you said. So you're going to say the mass of your copper. So maybe I had like 2.5 grams. I don't know how much you had. And maybe I want 3 sig figs because my scale read 2 decimal places. So you're saying that you're going to use the molar mass of copper, which is 63. I'm trying to see back there. It's kind of far for me. So I'm just looking on my periodic table. Thank you. 63.546. And this is always grams per mole. So grams cancels. So basically we're just taking mass, dividing by the molar mass, okay, to get your moles of copper. Okay. You shouldn't use this number. You should use your number. Okay. So however much copper you found. And then you should figure out for mass of your iron. So figure out how much iron was lost from the nails. Then you're going to divide by the molar mass of iron, which is 55.845 grams for 1 mole. So then that should be moles of iron. Okay, so we've done the first 4 boxes. We're doing okay so far? Oh yeah, sorry. So this is just on my periodic table. That's not something I'm memorizing. If I use that every day, maybe I would memorize it. Yeah, maybe eventually, but that's not something that because I have my periodic table, I can just look it up. Okay, so we're going to take the mass of copper, divide by the molar mass to get the moles of copper, take the mass of iron, divide by the molar mass to get the moles of iron. Okay, so that's the first couple boxes there. The next box is moles of copper divided by moles of iron, and we put the number with the correct sig figs. So I'm assuming that you should have 3 sig figs. Just check your sig figs, okay? Because our scale has 2 decimal places. Our copper is probably a single digit, right? Our copper is probably like 2 or 3 grams or 1 gram. Probably not 12 grams. Did anyone get more than 10 grams of copper for iron? Okay, great. So I'm assuming that you probably have 3 sig figs in this box because our scales have 2 decimal places. So this one's just the number moles of copper divided by moles of iron as a value. And then the next box says moles of copper divided by moles of iron as a whole number ratio. So you're just going to take the number here and you're going to round it to the nearest whole number. So, for example, if my number and if my ratio ended up being like 2.83, what's the nearest whole number? 3. Yeah. What if it was 1.05? What's the nearest whole number? Yeah. So this number, this box should have no decimal places. It should be rounded to the nearest whole number. Check with your neighbor. Does your neighbor get it?
Yeah.
Okay. All right. So let's look at this one. Why did the reaction stop? So you guys left yours for a long time. So why did it stop? What ran out? Did the iron run out or did the copper run out? I think the copper in the solution, right? The copper solution ran out, right? Did your nail run out? I think everyone had nail left over, right? So the reaction stopped because we used up the copper in the solution. Okay, so then we're going to think about what's happening to the atoms of iron and copper during the reaction. Does anyone want to explain to us what you think is happening? What's happening to the copper and iron atoms? So like, what did you measure at the end? What did you start with? What did you measure at the end?
How much atoms move from one to the other?
Yeah, so what you're saying the atoms are moving. So describe that a little bit further.
So it's saying like the atoms from the iron are moving over to the solution while building up the copper, making it so that this is right within the iron solution.
Yeah, so atoms are moving from the nail. Iron atoms are moving from the nail to the solution and from the copper solution into they're precipitating. Yes. And Spears, you had a name for that. What was the name?
It's a single replacement.
That's called a single replacement reaction. Good. So I will write that here. Let me erase this. So there's a few names you could call this. So this one is specifically called a single replacement reaction. This is also called, you can also just call it a replacement reaction. In the instructions, I think it says it's a replacement reaction. So you could just call it replacement. This is specifically a single replacement because we have two metals, copper and iron. This is also an oxidation reaction. Do you remember in chapter, I think 5, where we had one question that asked which will be solid and which will be aqueous, or oxidation and reduction, which one will be oxidized and reduced? This is an oxidation reduction reaction. We can also call that a redox. Redox. It's like an abbreviation. So any of those are true. Next question. What will happen if to the ratio of copper to iron if you had placed more nails in the beaker? So let's think about that. Would it change the reaction if you put more nails? No. Right. The copper would have run out still. So think about how many copper iron ions for how many iron atoms do we need? What was the ratio you found here? You found 1-to-1? So if you have 1-to-1, that means you need 1 iron for 1 copper. So if that's true, if you added more iron, that's not going to change the ratio, right? What if you stop the reaction faster? Will that change the ratio? Will it all of a sudden the reaction need more copper or more iron? No. So if we change the conditions, this is still going to need 1 copper for 1 iron. Does that make sense? Okay, give you a minute. It looks like we're writing. Oh. Okay, the next question, I think we're on 5, right? The last question here, or on 4, oops, sorry. Oh, accepted ratio. Oh,
Sorry.
I'm sorry for you, sorry. She needs some better friends, it sounds like. Just threw her backpack in my classroom. That's not very nice. Okay, so let's do number 5 first, because we're looking for accepted value. So we're going to write a balanced equation for the reaction. So our class, most of us did it with copper nitrate. So we're going to write the copper nitrate version. So we used iron. Then you put it in copper nitrate. Then we got out iron. And, oops, not iron. We got out copper. We got iron nitrate and copper. So, is this balanced? Yes, it's already balanced. Okay. We're missing phase symbols. So for every time you write a balanced chemical equation, if it's asking for the equation, you need to write phase symbols. So what phase was iron? Yeah. What phase was copper nitrate? Good. Dissolved in water. How about this one? Iron nitrate. Well, yes, it should dissolve in water. So when we went in there, yeah, your samples were evaporated. But this one should be aqueous because this one will dissolve and you can pour that off. And what about the copper? The copper was solid. Okay. Okay, so looking at this balanced chemical equation, what is the accepted ratio for copper atoms to iron atoms? Yes, so this should be 1 iron for 1 copper. Or I guess 1 to 1. Any way we look, this is 1 to 1. 1 copper to 1 atom, iron. And so then you're going to look at your differences. Is your ratio different than the accepted value? And that's okay. Especially our class, we ran out of material. We had to improvise. So write about what do you think happened? So did you have a higher ratio? That means you had more copper. So what could happen if you got more, what could cause your ratio to be higher in copper? So if at the end, if your copper was, if it was wet, or if you actually had some of your nail in the copper, that would make your ratio higher because it would look like there's more copper than there should be. Okay. Was there anyone whose ratio was smaller than 1? Okay, so then we don't. Oh, yours was. Okay, so can you think of something that would make your iron bigger than it should be? Because then your ratio would drop. So maybe if your nails for some reason had stuff on them, or maybe the nails were wet, or maybe I'm not sure if people use the same beaker every time. Like maybe if you didn't use the same beaker, your mass would be different. So think about, or like maybe your copper was smaller than it should be. Maybe some of the sample that you rinsed out was your copper, and for some reason it didn't settle to the bottom. That would make your copper smaller than it should be. So you just have to think through and reason through why would the ratio be different? Yes, Isabel. Oh, okay. Okay, let me come up. Okay, other questions? Okay, so, and we did these calculations before. So if you didn't do those, you can come during flex and we can talk about it. But we did do that already. So let's go ahead and we'll start working on Alex chapter 8. So I'm going to give our Alex chapter 8 topics. So did we talk about a like dissolved like last time? No. Nope. Okay, let's talk about like dissolved like. So when we're doing this topic, we're going to look for a few things. We're going to look for hydrogen bonding. Let's see. First, let me pull up. This one is another topic where we need to think about what kind of compound we have. So if we have an ionic compound, ionic compounds dissolve in polar solvents. This is because in an ionic compound we have a positive and a negative charge, and that interacts better with something that's polar, a polar molecule. So we can have something like a negative and a positive molecule, and that way it can break apart the ion. So ionic compounds dissolve in polar compounds. If we have something that's nonpolar, that's going to dissolve in something that's nonpolar. So watch out for nonpolar solvents. If we have something that is, it has hydrogen bonding, that's going to dissolve better in something else that has hydrogen bonding. Okay. When we're looking at hydrogen bonding, the easiest way to see is if we're looking for OH bonds. So if you can find an OH bond, you're going to want to pick a solvent that also has OH bonds. That's a quick tip.
Hydroxide dissolves hydroxide.
Yes, Okay, so let's look at some examples. And this is just if you can practice this one has lots of different types. So just get familiar with these different types of problems. Okay, so like dissolves like, we're looking for something that will dissolve this molecule. This is our solute, the thing that we're dissolving. This right here, you should also recognize it has hydrogen bonding. Good. So if we have something with nitrogen with two hydrogens, this has a hydrogen attached to a nitrogen, and it has a lone pair on a nitrogen. So if we have something like this, we're going to look for something else that has hydrogen bonding. So it can either have this nitrogen group, oops, only one lone pair, or an OH group. Okay, that will dissolve better in something that has hydrogen bonding. We can stabilize those interactions, those charges. Okay, so this one has hydrogen bonding. This looks pretty similar, but this molecule, we know water has hydrogen bonding. So this molecule is going to dissolve better in this water solvent because that's hydrogen bonding. Okay, next one. This one, oh, it has OH. So this is, if you can see OH, then you're going to look for something that has OH. So our solvent is going to be ethanol because this has OH groups. Do you see that? Does that make sense? Okay, next one. This one, I can see that I have potassium. Potassium is a metal. This is an ionic compound. Ionic compounds need a polar solvent to dissolve. I know that water is polar, okay? They're trying to trick you with this one. This one, remember, is tetrahedral. It has 4 identical groups. This one is nonpolar. Carbon tetrachloride is nonpolar. Okay, even though it has chlorine, that's not what we're looking at. We're looking at the type of molecule and if it's polar or nonpolar or hydrogen bonding. Okay. Let's go to the next one. All right, here we have, oh, we saw this molecule already. This one has hydrogen bonding. This one looks similar. This one is like ammonia. It has the 3 groups, but it has a lone pair on the top. I'm going to pick this one because neither of these has hydrogen bonding, but this one looks the most similar. So like dissolves like, I'm going to pick the thing that looks most similar. Okay. Next one. This one is a long carbon chain. This one has 1 + 4 + 1. This one's hexane. We have 6 carbons. This one's nonpolar. If I have a long chain of carbons, that's nonpolar. I'm looking for something that's nonpolar. This one is nonpolar. Carbon tetrachloride is nonpolar. It's going to be the best solvent for that. Okay, calcium. I recognize calcium as a metal. Calcium chloride is an ionic compound, so I need something polar to dissolve that. So methanol, we have this OH group that's going to make this molecule polar. So methanol will be a better solvent than carbon tetrachloride because carbon tetrachloride is nonpolar. I need a polar solvent to dissolve ionic compounds. Okay, how are we doing? Do you want to do another example? Okay. All right. This is our exception. This is an ionic compound. You need to recognize anytime we have NH4, that's ammonium. Ammonium is an ion. So this is an ionic compound. Okay, it doesn't have any metals, but you need to start recognizing this as ionic. If we have an ionic compound, we're looking for something polar to dissolve it in. Water is the best polar solvent. Okay, ionic, I'm going to dissolve it in something polar. Okay, next one. Oh, look, we have another exception. This is ammonium bromide. Bromide is ionic, even though there's no metals. So we're looking for ionic compound. We're looking for a polar molecule. So this is going to be the best molecule because it has OH groups. That's going to make one side negative and one side positive. Ethanol. Okay, next one. We have OH groups. Anytime you have OH groups, look to see if your solvent also has OH. Well, water is just OH, so that's going to be our best solvent. Okay. So there's just lots of different versions of this question, so make sure you can reason through that. Do you want to do another one of those, or are you ready to move on? Move on? Okay. All right, next question. We did that one. Okay, let me pull up I have a list of topics that we need to get through. Okay, the next one is understanding how solubility varies with temperature and pressure. So this is mostly an intuitive question, but we have to use some reasoning. So before we do this one, let's write down a few tips. So we are looking at how solubility varies with, and there's two categories. So solubility, we're going to look at a solid dissolved in a liquid. And for this one, we're going to look at temperature. So think back to the last time you made syrup. So what do you do when you make syrup?
Put sugar in hot water.
Sugar and hot water, good. So you're saying that you're increasing the temperature. What happens to the solubility of the solid of the sugar if you increase the temperature? Yeah, increases, perfect. What happens if you decrease the temperature? Yeah, decreases. Okay, great. Okay, so that one's really intuitive. The other one that we're going to think about is a gas dissolved in a liquid.
Carbonation.
Yes, like carbonation. So I think carbonation is going to be the best thing to think about here. So we're going to look at, we're looking at solubility of the gas.
Could be wrong, but I feel like it's the English for this one.
It is for temperature, you're right. So temperature, if we increase the temperature, the solubility decreases for a gas. And this is why it's so important that we don't let the oceans warm too much, or there won't be any dissolved oxygen for creatures that live there. So if we decrease the temperature, then the solubility increases for gases. Okay. The other thing that we have to think about for gases is pressure. And this is where you can use your intuition with pop bottles. So if you increase the pressure of a system that has dissolved gas, what do you think will happen to the solubility? Which one? Yeah, it increases. So if you think about your pop bottle and you open the pop bottle, you're releasing a whole bunch of pressure. They had to pressurize the bottle so it will hold carbonation. And that's why if you open your pop bottle, then you only have a few days before it becomes flat, right? So increase your pressure, increase the solubility of your gas. So opposite is true if you decrease the pressure. So if you open your bottle, the solubility of that gas decreases and the gas will start coming out. Okay, so
means opening the pop bottle in space would be interesting because you got 2,000 forces.
oh,
Be interesting to see.
yes, interesting. Interesting to think about. Good research question. Okay, so these questions are based on these trends that most of them are intuitive that you know already. So this one says, a student sees tiny bubbles clinging to the inside of an unopened plastic bottle full of carbonated soda. The student squeezes the bottle. So what are you doing when you're squeezing the bottle? Increasing pressure. So you're increasing pressure, you're increasing solubility of the gas. So what should happen to the bubbles? So your bubbles should go away because the gas is getting more soluble. So because you're increasing pressure, the bubbles will shrink and some may vanish because you're dissolving them by increasing the pressure. Okay, a student sees tiny bubbles clinging to the inside of a can, blah, blah, blah. The student opens the bottle and a gas under pressure escapes. What will happen to the bubbles? Bubbles will grow, good. Because you are decreasing the solubility. You release the pressure. Now it's just atmospheric pressure. It's not extra pressure. So now the bubbles will they will start being unsoluble and they'll come out. Okay, questions? Does that make sense? Yes.
So, seeing as it's likely that a lot of gases are soluble in liquids, is there a chemistry reason that we use carbon dioxide instead of like oxygen or something like that?
Oxygen is flammable, so that's probably the best reason to not use oxygen.
Food blowing up.
That might be exciting. Maybe you could create a business based on oxygenated soda. Yeah, carbon dioxide is inert, pretty inert, so I think that's probably why.
There's also oxygen in carbon.
Oh, I think he's talking about like O2.
Oh.
Like if you, yeah. Interesting. Okay, good question.
Chemical reason right there. Seeing as it's also.
It's probably cheap too. I don't know. I would imagine that it's cheap. I don't know. I was thinking like could you use argon or something, but argon is probably expensive to bottle. Okay, next one. A pair of 100 milliliter samples of water are taken from a well, and so you pull one sample out. It's initially at 32 degrees Celsius, and then you pull out the second sample and it's at 42 degrees Celsius. So what you want to look at is the initial temperatures and the final temperature. So the final temperature is 20. So that means the temperatures both dropped to 20. Does that make sense? So if the temperature goes down, what happens if your temperature, okay, we start at 42 and 32. So we end up finding a precipitate in the one that dropped from 32 to 20. So the sample at 42 heated up higher than the sample at 42 or 32. So this one can dissolve more sample because it ended up at a higher temperature. And then it dropped to 20. So the sample at 32, if the sample at 32 has a sample, then the sample at 42 also should have a sample. And it should be bigger because it dropped a higher temperature, a larger temperature drop. You guys are giving me blank stares. Yes. A higher temperature, you were able to dissolve more. Does that make sense? Okay. Okay, next one. Rock candy is formed when excess sugar is dissolved. So this person dissolves sugar in 500 milliliters of water at 70 degrees Celsius, and the same thing but at room temperature. So which sample will dissolve more sugar? Higher temperature will dissolve more. Good. Because if we increase the temperature, our solid will dissolve more. And then this person lets it sit at room temperature, and so we're going to expect more to come out of the sample that we were able to get more to dissolve in.
I'm sure if there is actually like a real world situation where you would get more dissolved in the other way, because it says it's likely, but it's not certain.
Yes, I actually do have an example. So, maybe not specifically to this, but I was interviewing people who were working on radioactive waste, and they were saying like they were doing experiments, so they're trying to figure out how best to store it.
Yeah.
But it was like behaving in really weird ways. So we have this device called a sonicator, and it like sends sound waves, and it like breaks the pieces up, and that's supposed to dissolve your sample. And they were doing that, and it was like crystallizing. Or they were like trying to flow it through pipes to get it to store the storage area, and it was like crystallizing in the pipes, and it like shouldn't have, like based on what we know. So I think that there is always possibility that right there
just would act weird.
Yes, and then you have to understand. So they're trying to understand it. They're trying to model it to figure out the best way to deal with this material. So that was kind of interesting. Yes. Okay, let's do one more. Okay, this one says there's a pop can, and one has been stored at 32 degrees Celsius, and one has been stored at 8 degrees Celsius. So based on what we know about dissolved gases, which one will the gas dissolve in better? Yes, good. So colder temperature, gas dissolves better.
So A is probably going to have a louder fizz?
Yes, so if we open them, yes. This one will be louder because it can't dissolve as good.
So it's got more than just floating around.
Yeah, yep. Okay, that's our prediction. Great. Okay, and then the salt mine. Okay, this one's a little bit different. Look at, again, we're looking at the temperature. So sample A starts at 42. Sample B starts at 8. So they're both going to go to 20, but one is warming up and one is cooling down. And it says a sodium precipitate is seen in sample 1. So what do you think about this sample? Will we see something precipitate? No, why?
Because it's becoming more soluble. You've already got everything dissolved in it.
Yes, perfect. The temperature is increasing, so it's going to be more soluble. Good. So no precipitate in sample 2. The temperature is increasing, that increases the solubility. Okay, I think we've gone through most of the types, so we'll let you keep working on those. This is one that you have to practice so that you're familiar with all the examples and you can reason through all of them.
Are these like the exact ones that you feel?
Yes. So like you can get random one of these. Yes. From what I remember, yes. Okay. Or if you can do these, I know that you can do the ones on the test. They're not like different. I think they're the same.
Same concept.
Yes, I'm pretty sure they're the same. Okay, next question. We need to get through a few more so that we don't have to do so many next time. The next one is calculating mass concentration. Let's see if we can get through at least this one, maybe one more. So let's go to, this one's not too bad. Calculating mass concentration. So this topic, I always look at my units first. And the box is telling me what it wants. It wants grams divided by liters. So then I need to go through the question and look for, okay, I have grams and I have milliliters, so we need to convert that to liters. Okay, but I can do that. I know that if I just move my decimal 1, 2, 3, I'll get liters. So let's do that really quick. So grams, 0.135 divided by, I'm going to convert milliliters to liters in my head, so that's 0.2. So 0.54 grams per liter. Oh, I have an extra. Okay, also let's see. This one has 3 significant digits. This one has 3. So my answer has to have 3 significant digits. So I need to add a 0 at the end. Now my answer has 3 significant digits. Okay. This is one on the test. It won't tell you how to round it. So you need to recognize the sig figs. I think you guys are getting good at that. So I'm not too worried about that. Okay, let's do another one. Some of these have a little bit different units. Okay, this one's a little bit different. Maybe we need to show our word terms for this. Yes, deciliters. So no one ever uses deciliter. Maybe someone does. I don't know. Maybe biologists use deciliters. Just kidding. I'm glad there's biologists. Okay, so this one wants grams per deciliter. Okay, well, we have grams. Great. So let's just write that down. We're looking for grams per liter, or deciliter, excuse me. Well, we have grams, so let's just write that down. And we don't have deciliters, we have milliliters. Okay, so I'm going to convert. So the thing that makes the most sense to me is going from milliliters to liters, and then liters to deciliters. So that makes the most sense in my head. If you have a different way to do that, feel free to do that, okay? But I'm going to go from 500 milliliters. That's the same as 0.5 liters, okay? So I know there's 1,000 milliliters in 1 liter. Then I also know that there are 10 deciliters in 1 liter. So to get from liters to deciliters, I'm just going to move my decimal over 1, and that will give me to deciliters. So I'm going to move my decimal over 1. So 0.5, let's see this. 0.5 liters is the same as 5 deciliters. That makes the most sense to me. There's also these little buttons in Alex. If you look at data, it has the SI prefixes, and you can work through those also. So if that makes more sense to you, you can use those. This is the method that makes the most sense to me. Okay, so that we decided there's 5 deciliters, and there's 119 grams, and then we just come over to our calculator. $119 divided by not 0.5, 5. Oh, 23.8, and we got to check our sig figs. There's 3, and was there 3 here? Oh, I can't see. 3, so 23.8. Okay. All right, let's do one more topic, and then we'll be done for today. So the last one we're going to do is calculating molarity using using solute moles. So this one is similar to the one we just did. Okay, so we have some numbers. A chemist prepares a solution by measuring out 55.3 micromoles of potassium iodide. And then they fill that to a 50 milliliter graduated cylinder. Calculate the concentration in millimoles per liter. So again, the box is going to tell you what units to use. This one says micromoles, so we need to convert micromoles to millimoles. So let's put that on our whiteboard over here. So we're trying to get millimoles per liter. And we start with 5.3 micromoles. So I need to convert this to millimoles. If I go to my Alex data and look at the prefixes, micro is this weird U. It's a mu. Micro is times 10 to the minus 6. So instead of writing micro, I'm going to write times 10 to the minus 6. That is micromoles. Okay. And then I'm going to convert this number, so 55.3 times 10 to the minus 6 moles, and to convert it to millimoles. So I know there's 1,000 millimoles for 1 mole. Oh, so that's upside down. Oops. So 1 mole gives me 1,000 millimoles. So this is just like milliliters. 1,000 milliliters is 1 liter. Okay. So that prefix is the same. So I'm going to take this and multiply by 1,000, and that will give me millimoles. And then I'm going to divide by liters. This one is 0.05 liters. Let's just convert that in our head. This has 2 sig figs. Again, this one won't tell me how many sig figs to keep on the test. So this has 2, so my box is going to need 2 sig figs. All right, let's find the calculator. So I'm going to do micromoles to millimoles first. So 55.3 times 10 to the negative 6. So that's micromoles. If I multiply by 1,000, I'll get millimoles. And then I'm gonna, divide by number of liters. I'm going to convert this to liters in my head. So I'm moving the decimal 1, 2, 3. 0.05 liters. Okay, and then this is my number. And we can only have 2 sig figs, so I'm going to put 1.1. Okay, let's do one more. Okay, this one's looking for moles per liter. We have micromoles and milliliters. So let's write down what we need to find here. So we're looking for just moles, and we have micromoles. So I'm just gonna write 49.9 times 10 to the minus 6. That is micromoles divided by milliliters. I need that to be in liters. I know that because it tells me that should be in liters. So I need to convert that to liters. So 0.4 liters, and that will be my answer. So let's see what we get. So 49.9. Oh, it's not typing. 49.9 times 10 to the negative 6, because it's micro moles. Now it's moles. Divided by 0.4 liters. Okay, and this is a really small number. So I'm going to, on my Alex calculator, I'm going to push this scientific button, and it will automatically put it in scientific notation for me. You can also figure that out on your personal calculator if you use that. Okay, and then let's see. This one has 3 sig figs. This one has 3 sig figs. So my answer needs 3 sig figs. I'm just going to copy paste my number. And then let's get 3 sig figs. Let's see. So we've got 1, 2, 4. So this needs to round up to 1, 2, 5. Oh, there's a 5 there. Perfect. Okay. Questions on this one? So this one's just being familiar with the units that come up and converting and then dividing the correct units. Okay. That means we have 10 minutes left. So I'll let you just work and then we'll finish the last topics next time. We're also going to talk about the lab. So we will do a lab next Monday. We'll talk about Lab 7 and then we'll do the last 3 topics. Cool.